Okay, so I think we can start. So welcome everyone to this machine learning coffee seminar. This is the last seminar of this year actually, and we will come back in January or plan to. So we will have a really exciting talk by Juho Kannala from Aalto University about visual location and odometry for mobile devices and machines. So and if you have any questions during this talk, just you can write them in the chat and I will then read them aloud. Okay, so Juho, please.
Thanks for the invitation to talk in this seminar. So in this presentation, I will cover some papers that we have done during the past years, and this is the outline of my presentation. So first I will tell a little bit about the background and motivation why we are studying these problems. And then there are two parts in this presentation. The first part deals with tracking of mobile devices, and there we present our approach for solving this visual-inertial odometry problem. And the second part deals with the positioning of mobile devices or machines, and there we will discuss approaches for visual localization and mapping, and briefly present our CVPR paper from this year. And then I will conclude with some thoughts about future research directions. So like probably many of you know, these problems of tracking the motion of mobile devices in real time, and then on the other hand localizing the device with respect to a pre-built map or model, they are very relevant problems for certain applications, like augmented reality, for example. And this kind of an augmented reality use case is illustrated here in the picture. So we may have mobile devices and then we use them in some predefined environment, and we would like to show augmented content in the live camera view. And in order to do this in a realistic manner, we need to be able to precisely position the device with respect to this environment, and then also track the motion of the device accurately in real time, so that this augmented content appears photorealistically in the live camera feed. Another application for these kind of techniques are autonomous machines. So for example, we could have some autonomous robots deployed to some manufacturing site or some indoor environment, and the echo motion estimation and localization of these machines could be relevant also. Then the question is that why to study these problems? Aren't they already solved? And there are already solutions that work in some use cases, but the particularly challenging situation is this kind of mobile phone use case, where the sensors in the device are somehow limited, and they need to be relatively cheap and consume little energy, and this makes the problem challenging. And this is illustrated here with a short smartphone video clip. So this is a video clip taken with an iPhone. So we record the accelerometer from the device, the gyroscope from the device. So those sensor readings are shown here in top, and then we also use the video camera. So if we assume that we would have these three sensor modalities, so accelerometer, gyroscope, and video camera, all that information is visualized here, and we can see that it's not necessarily always easy to localize the device. Some of you may already recognize where this has been captured, but if you are not very familiar with Helsinki, this could be, for example, any train station in the city, and there is not that much information about the location. And there are also multiple moving objects. There is motion blur. So also the tracking is maybe relatively challenging. But this illustrates the problem context that we are trying to address. And the first part is this kind of tracking or odometry problem, where we just want to track the relative motion of the device in real time. And when we are able to track the motion, we can then fuse several measurements and use sequences of measurements for localization. And I will talk about localization in the end of this presentation. And this odometry problem is solved based on sensor fusion. And here we use smartphone grade sensors. So current smartphones have actually quite many sensors. Some of them are listed here, but in this presentation, we focus on using the 3 sensors here indicated with blue color. So we have 3-axis accelerometer in the device, 3-axis gyroscope, and then a video camera. And so these sensors enable developing this kind of visual inertial odometry approach for tracking the motion of the device. But let's first start from inertial navigation. So let's assume that we just have the accelerometer and gyroscope and we don't yet have a video camera. So this basic principle for inertial navigation, it's old one and it has been used in many applications, for example, in submarines or aerial vehicles already long time. And the idea is that when we are able to measure accelerations, we can get the velocity by integrating the accelerations. And then the change in position is the integral of velocity. And in the mobile phone, we can observe acceleration and angular velocities using the accelerometer and gyroscope of the phone. And by integrating these measurements, we can first get the velocity, and then further integrating the velocity, we can get the change in position. But this is actually quite challenging, especially with low-grade sensors, such as those in these kind of lightweight mobile devices. So all inertial navigation systems suffer from integration drift, which means that even very small errors in the measurement of acceleration and angular velocity will cause progressively larger errors in velocity because of the integration. And then the second integration causes even greater errors in position. And these challenges are further amplified by the fact that the dominant component what the accelerometer senses is gravity. So if we have even a slight error in orientation, this makes the gravity to leak. So we erroneously think that some part of the gravity is actually linear acceleration. And the sequential nature of this problem makes the errors accumulate. So without any other information, even this kind of very small sensor noise could cause huge drift in the position over short periods of time. And these problems are particularly challenging on smartphones because the inertial measurement units in these devices, they are cheap and small. The signals are noisy. There may be also unknown calibration parameters that may also vary in time. And the sampling frequencies are relatively low. So you can get these signals with 100 Hertz frequency, whereas these kind of industrial grade or military grade inertial measurement units provide the signals with with much higher frequencies. But with some extra information, this inertial navigation can be made to work even with smartphone sensors. And here is just very briefly the outline of our approach. So what we measure from the device is the accelerometer signal, here denoted by symbol A, and the gyroscope signal, here denoted by symbol omega. And the dynamical model determining the movement of the device is based just this kind of classical dynamics equations, where we get the change in orientation by integrating the angular velocities from the gyroscope over time. So here this Q is the quaternion that indicates the orientation of the device, and the change over time step delta t is obtained by integrating the gyroscope signal over that time period. And then we get the change in the velocity in the word frame when we rotate the accelerations from the device frame to the word frame. Then we subtract the gravity, which is indicated by G here, and then integrate it over the time step delta t. So that gives the change in the velocity, and we get the new velocity by adding the change to the old velocity. And finally, we get the change in pose. Here, pose is, or this P is the location, so it's X, Y, and Z coordinate of the device, and we get the change by integrating the velocity over the time step. And we can solve this kind of state estimation using a nonlinear Kalman filter, which combines the model with the data in probabilistic way. So here the data are the sensor measurements from the accelerometer and gyroscope. But like mentioned, even a small error and noise in the signals will rapidly accumulate and cause drift that makes this kind of direct integration using nonlinear Kalman filter non-practical. So we need some additional measurements or constraints. And here is a list of possible additional information that can be used. So for example, if we can automatically detect that the device is completely stationary at some points, for example, if it's rigidly attached to a moving platform that stops every now and then these kind of zero velocity updates can be used, and they can be enough to constrain the estimation and prevent the accumulation of errors. One can use other external information like position fixes coming from some localization method or loop closures that are obtained. So we notice that we revisit some place that we have visited earlier during the motion sequence. But the additional information that we will, and one can also use these kind of priors like as pseudo constraints, that we know that there cannot be arbitrarily large velocities. But the additional information that we have mainly used comes from the camera. So we take into use also the monocular video camera that exists in these devices, and we move from a pure inertial navigation to visual inertial navigation. And this problem is called visual-inertial odometry in the literature. So we combine the visual information with the inertial data, and this turns out to be a practical solution that allows to constrain the accumulation of errors in the inertial navigation. And the visual information comes in the form of feature tracks. So we see the same visual features in multiple frames during the motion, and these visual feature tracks, they provide constraints that that can be used as additional information in the nonlinear Kalman filter. And these sensor modalities, they are complementary. So there exists also methods that are only based on cameras, and these are these kind of pure visual odometry methods. But this visual inertial odometry has the advantage that the accelerometer allows us to infer the true scale of the motion, whereas pure monocular visual odometry can only give the motion up to scale. So the scale can be arbitrary. And another benefit from the inertial sensors is that we can be robust against short occlusions. So if the camera lens is briefly occluded, we can still track the motion thanks to the inertial sensors. But because of the rapid accumulation of errors in the pure inertial navigation, these occlusions should not be too long. But also this visual inertial odometry suffers from challenges on smartphones. So also the smartphone camera is not very optimal for this kind of use case. So it typically has a small field of view, and the cameras have a rolling shutter, which means that it's not optimized for this kind of visual inertial odometry use case. And because we want to do this in real time on board of the device, the limited computational processing power may also be a challenge. And the use cases can be also quite challenging. So this kind of handheld movement can have quite rapid motions, and one cannot assume this kind of smoothness that could be the case if the device would be moving on a field vehicle, for example. And in these kind of use cases that I showed in the video clip in the beginning, where, for example, the person is moving in a crowd, where the other moving objects may briefly cover the lens so that the camera does not see the static environment. So this may turn out to be a challenge. And the method needs to be robust against these kind of disturbances. And also if the environment where the camera is moving does not have many visual features, then this complementary nature of the sensor modalities is beneficial. So the approach that we have developed, we have named it as probabilistic inertial visual odometry. And here we use this, we don't talk about visual inertial odometry, which is the most common term. We have switched the order of these words, so we talk about inertial visual odometry, and this is because we build upon this kind of classical inertial navigation approach, whereas previous methods for visual inertial odometry have been more like visual first methods, where they have been built on pure visual odometry. But this makes these previous methods quite sensitive. So if there are occlusions or other challenges, so that one cannot track visual features all the time, then they may be very sensitive, and the tracking may break. But we treat this visual information as a signal of opportunity. So we use these visual features when they are available, but even if they are not available, we can track the motion over short periods of time based on the inertial sensors. So one can think that the camera provides these kind of bursts of high quality odometry when it sees something that is visually distinguishable. And it turns out that that kind of visual information is sufficient to constrain the inertial navigation and prevent the errors to grow. And this can lead to quite accurate estimation. And we can also learn the calibration parameters for the inertial measurement unit online. And that is quite relevant here because the sensors are not very well calibrated and the calibration parameters may change in time. So the approach is based on a state space model, which is solved by an extended Kalman filter, and the dynamics are driven by the inertial measurement unit signals. So we do pose augmentation on every new frame. So this works in an online fashion. So we have all the time the current estimate, and it is based on the information that we have seen so far. And we use these visual feature tracks, so the measurements of the same points in the different video frames as measurements in the extended Kalman filter model, and visual update is performed per each feature track. And we can react suspicious visual updates. So if we see something that some visual feature that is tracked, but which is not moving according to our understanding of the device motion in a static environment, we can react these kind of erroneous visual updates. So we can notice if certain visual features are tracked from another moving object and not from the static background. And this makes the approach quite robust. So I will show one example where we run this our approach in a mobile phone. So the data capture setup is illustrated here. So we have 4 different phones, or actually 3 of these phones are similar. And one of them runs our method, one runs the Google AR Core, and one runs the Huawei AR Engine method. So these all 3 are visual inertial odometry approaches from different providers. And then there is also an iPhone which runs the ARKit approach, which is Apple's visual inertial odometry approach. And then we have also this kind of Intel RealSense sensor, which is actually a stereo sensor. So this Intel RealSense device has 2 cameras, whereas all these mobile phones have only 1 camera. And here these phones are now placed on the car, and what we show here is the trajectory estimated by our method, which is the blue curve, and the gray curve is the GPS-based ground truth. So in this kind of an outdoor setting, GPS works quite well, at least in this environment, and it does not, of course, suffer from this kind of long-term drift that these kind of sequential methods may suffer from. So our approach does not use the GPS as a measurement at all. So it's only based on the camera and the inertial sensors, and it runs real time on the smartphone. So here we see that when the car slows down the speed when it's approaching a turn, there are these kind of negative accelerations that here appear in the track as if the car would be moving briefly backwards. So that's not the case, of course, but this shows that the inertial sensors are very important part of the signal. but overall the drift is quite small. So even if we drive relatively long distances, there is not much drift. So besides the odometry, there is actually a visual SLAM approach also running. So here, when it was coming back to a region where it was driven before, there was a one loop closure here, which caused this kind of jump in the trajectory. Sorry, I will go back to the. So here is the trajectory that our method provides, and we visualize also the trajectories from the other devices. So there is the Intel trajectory, AR engine trajectory, AR core trajectory, and then the trajectory from the AR kit. And it seems that all these other methods failed in this case. Part of the reason might be that they have not been designed for this kind of field vehicle use cases. So they have been mainly designed for this kind of handheld motion and AR use cases in small spaces. But still, our method performs also in those kind of use cases. So we think that this is quite promising, that it generalizes to this kind of autonomous machine use case as well. And here we see also the 3D nature of the trajectories. So in many of these alternative approaches, there is significant drift also in the vertical direction, whereas our curve is flat. So the terrain is here quite flat. So that's the desired shape. So I have also other examples here, but I will skip them because of lack of time. But these examples are available on our project page, which is this one shown here at the bottom. So this odometry work is done in a project funded by Business Finland. And besides me, there are several other members in the team. So the project is led by Assistant Professor Arno Sulin, and there are also several other experienced researchers involved. So to recap the visual-inertial odometry part, so this method that we have proposed seems to be quite robust to occlusions and dynamic objects in the scene, and it provides improved performance in challenging conditions. So we think that this is quite promising starting point for certain applications. And I will still talk a little bit about also visual localization, which is the other theme. So in many use cases, we actually need to solve both problems. So this odometry problem provides the relative motion of the device, but this motion is in some arbitrary coordinate frame and not associated with any global coordinate frame or any map. But what we actually usually want is that we want to also localize the device and put this track trajectory to some map coordinates, as shown here. For example, if we have an indoor map, we would like to know that where we are in the building. And we have studied visual localization methods where we take an image with the camera of the mobile device, and we would like to position the device based on the information in the image. And when we can localize certain image, then we can place this entire trajectory to the coordinates, to the map coordinate frame. And this visual localization first needs visual mapping. So we need to take some training images from the environment. For example, we capture a video sequence from the environment and we compute the corresponding camera poses and that 3D point cloud that represents the 3D scene structure. And this kind of 3D point cloud is then our visual map. And there are two main approaches for computing these kind of visual maps. So structure from motion can do this from unordered image collections, and then simultaneous localization and mapping techniques utilize the fact that they know that there is a sequence of images coming from a moving camera. And I will show a brief video which illustrates this kind of SLAM-based mapping approach for getting a visual map from a small indoor environment. So in this video, we have a SLAM approach running on a smartphone. The smartphone has also a depth camera, and thanks to the depth camera, we can get this kind of dense point cloud from the environment. And the phone actually runs this kind of visual inertial odometry approach, so that provides the tracking information. So thanks to the tracking and the depth camera, we can fuse these different depth maps to a common coordinate frame. And then this SLAM system also establishes loop closures, which prevent this kind of long-term drift. And all this can be run on a smartphone. So in the end, we get this kind of 3D point cloud as shown here. And this kind of point cloud can then be used as a visual map. So if we later come to the same environment with a camera and we take a photograph, we can localize this photograph based on the map. For example, we can obtain feature correspondences between the new image and the map and use them to solve the pose. So the problem in visual localization is to estimate the camera pose for a query image with respect to the visual map. And this needs to be done at test time very quickly. And there are several approaches to this problem. So there are methods based on local feature correspondences, where we try to obtain some corresponding points between the query image and the previously built map. And then there are these kind of scene coordinate regression methods. And in the last part, I will talk about one particular scene coordinate regression method that we have recently presented, and it was presented in the CVPR conference last summer. So this scene coordinate regression refers to formulating the visual localization problem so that we assume that we have some 3D scene like the one illustrated in the point cloud in the previous video. And then we can define this kind of scene-centered coordinate frame and define the scene coordinates for all the points in the point cloud. So we have X, Y, Z in the scene coordinate frame, and those coordinates are here illustrated with red, green, and blue color. Then for the training images which have been registered with this 3D model of the scene, we can pose this localization problem so that we want to regress the 3D coordinates for each pixel in the training images. And this can be done with a neural network. So the neural network tries to predict the X, Y, Z for each pixel in the training images. And for the training images, we know those locations because of the reconstruction process that we have run during the mapping time. And it turns out that this kind of neural network-based approach actually generalizes for unseen test images as well. So when we get a new unseen query image and we evaluate it with the scene coordinate regression network, it is able to predict the scene locations for the input pixels. And from these predictions, we get these kind of point correspondences between the pixels of the query image and the 3D points in the scene. And then the pose can be solved from these point correspondences using classical methods of computer vision. So we solve the perspective endpoint problem using the Ransack framework. And there have been scene coordinate regression methods already before, but we propose this kind of particular approach, which is based on hierarchical scene coordinate regression. So we divide the 3D scene, so this kind of 3D point cloud, hierarchically into clusters. So at the first level, we have a small amount of clusters indicated by the colors here in this second image on top. Then we further divide these original clusters to more fine-grained clusters, which are illustrated here on the second or on the third subfigure. And finally, we have the scene coordinates, which are the XY set for each point. But this kind of coarser subdivision actually helps in the scene coordinate regression. So for a given input image, we first try to predict, we take into account all the pixels in the image and try to predict the region labels for the pixels. First at the highest level of the hierarchy, and then at the finer level of the hierarchy. And finally, we predict the scene coordinates given the predictions of these regions. And this turns out to be useful in practice. And how we do it is done with this kind of neural network architecture, where on the left-hand side, we take the input image, which is color image with 3 color channels and with H pixels high and W pixels wide. And then we, at the highest level of so also this network has this hierarchical structure, so that at the highest level, we first predict the labels for the coarse regions, and then use these predictions to condition the prediction for the finer level region labels, and finally use all this information as additional input to predict the scene coordinates. So this way we can utilize both global and local information for better generalization of the scene coordinate predictions. But I will not go into further details of this architecture because of lack of time. But I will just end my presentation by showing some results. So we have evaluated this localization method with a standard data set provided by Microsoft Research, where there are 7 small scenes, and each scene has this kind of 3D model obtained from training images. And then there are some test video sequences where the frames of the test video sequences need to be localized with respect to the pre-built 3D model. And here is one test video sequence illustrated. So what we will show in this video is that on the left side, we show the raw color information from the current input image. And on the right-hand side, we render the 3D visual map from the viewpoint that has been estimated by our localization method. And if these seem to align well, then the localization is accurate. And here we localize every frame independently, so there is no tracking or odometry applied here. So here we see that when the camera moves and we get new video frames, each one of them is localized so accurately that there is not much visible jitter or this kind of errors. So the 3D model rendered from the estimated pose overlays very well with the image. And there are additional videos available from our project page. So to conclude, so I have very briefly presented contributions for both tracking and localization. So I presented this kind of probabilistic inertial visual odometry approach, and then this kind of hierarchical scene coordinate regression method for visual localization. And here these two things were completely separate. So there was no fusion of tracking and localization. But ultimately, tracking and localization should be, of course, integrated. So for many practical applications, we need both at the same time. And we are planning to look into this kind of system level approach probably later. And there are these kind of methods could be used for many applications. So if these systems would work well, they could enable more robust and precise navigation for autonomous machines, or improved inside-out tracking for virtual reality glasses, and also 3D-aware mobile applications and immersive augmented reality applications. Okay, and here are some references, and I will finish with this slide. So thank you for listening, and sorry, I think I exceeded my time a little bit.
Okay, thank you for sharing the thoughts. So we still have time for discussion. Any questions?
Was there a question I didn't hear very well?
Yes, but I have a question. So
sorry, Markus, I guess your voice is somehow missing, or is it only my computer? Was it so, Juho, that you can't hear Markus either?
I cannot hear very well. There is some disturbances in the
Okay, can you hear me now?
Now, yeah, now.
Okay, excellent. Okay, so are there any questions? And if not from others, so I have a sort of like a trivial question. I wonder, are these problems in general solvable or identifiable?
So, of course, I mean, this localization problem depends on the visual content, what you see. So if you just see like a white wall, of course, you cannot localize yourself. So, I mean, the intuition works quite well. So if you see if you can localize yourself as a human being, then you probably see enough like distinguishable visual information. So here the idea is that if you combine localization and tracking, then you don't need to all the time localize yourself, because the tracking allows you to cover the gaps. So for a practical system, then if you can all the time track your motion, then as soon as you see something that is visually distinguishable and in your map and sufficiently unique so that you can uniquely determine your pose, then you get your location, and from that onwards you can stay on track if your odometry is robust. So that is like the idea how it should then work in practice.
Okay, thanks.
Good morning, everybody. I have another question. Can you hear me? Can you hear me? All right. Yes. So first of all, thanks for the great presentation. Really intriguing. I was wondering, like, if we move from a smartphone to a fixed camera, say in a boat, for example, and imagine a busy harbor, waves shaking the boat a little bit, fixed mounted cameras on both sides and on bow and stern of the boat, and you would need to park the boat automatically to a free slot in the harbor. So how stable your platform needs to be for this IMU-based navigation to work? I mean that, like, compared to a car that is more or less stable laterally, boat might be shaking a little bit when there is heavy weather. So do you see having a suitable set of sensors, this could work in a boat, for example?
Yes, I think so. So I had some example videos, so you can find them through the links on the slides where we show this kind of tracking with handheld devices. And I think that the handheld motion is not that different from the motion of a boat or some flying vehicle. So I think that those kind of large devices, whether they are on sea or in air, they move typically more in a more stable manner than a human hand in an arbitrary movement. So I guess it should work. So the benefit, of course, here is that you don't need to assume anything about the motion. It can be a field vehicle, locomotion like human walking or waving the device in the hand, or a device flying in the air if it just can see something that is static in its environment.
What I see here would be a great benefit is that you, if I got it right, you don't need any sort of pre-given map of the area, because this harbor problem, for example, the scene changes all the time. Boats come and go, and slots become free and become like occupied. And then, if you could just get a shoot of video sequence of a slot that is free, I guess that would be enough to form the 3D.
For the localization, you need some kind of a map, and I guess you then need to build a model to recognize like an empty slot, and that should be then like use case specific. And but I mean, the relative motion estimation is quite generic and can be used to model the movement of the machine. But then if you need to drive to some location, you need to somehow have a map or understanding about the environment based on some kind of a map.
Okay. All right, thanks.
Okay, so we are running out of time. So I want to thank again Juho for the interesting talk, and I want to thank the audience for the attention. And yeah, so as I said, this is the last session of this year, so we won't come back next week, but we will come back in January. Okay, so thanks everyone and have a nice day.